This is a parameter. By itself, it's just a single humble number, a basic unit of knowledge. Look at it. It doesn't look like much. And you're right, it isn't. But here's what's wild. In theory, enough of these tiny pieces of mathematics can resolve into something as complex as human language, visual intuition, even creative thought. In modern state-of-the-art models like GPT-4 or Gemini, we aren't dealing with a handful of numbers. We're dealing with trillions. It's an absurd scale, and frankly, it's getting a bit out of hand. As these models grow, they hit what we call the scaling wall. They eat through VRAM like it's kibble. Inference becomes painfully slow, and we're left with a black box that is almost impossible to interpret. More parameters just means more bloat this way, instead of more intelligence. The solution can't be just bigger hardware, right? We've been improving hardware for decades, and these bottlenecks surely cannot be resolved by forcing computational power to keep up. Well, fortunately, the solution is something different. Tensor decomposition. It's the art of looking at these massive, redundant structures and extracting their hidden, essential core to the patterns that actually carry information. But why go through the trouble of using tensors instead of simple, flat matrices? Because the real world isn't two-dimensional. If you flatten a recommendation system into just users and items, you lose the context of time. Tensors let us natively exploit these multi-way correlations without breaking the underlying structure. To truly master this, we need a formal language. Think of it as a hierarchy of complexity. We start with a scalar, a single value, rank 0. A list of these becomes a vector, requiring one index to navigate. A grid becomes a matrix, needing 2. But when we go beyond that, into 3, 4, or n dimensions, we just call them tensors. Yes, just tensor. These are multi-way arrays, where each direction is called a mode. It's an elegant piece of math that allows AI to see relationships that would be otherwise invisible in a flat world. Imagine you're Netflix, and you want to recommend movies to people. Not generic recommendations, personalized ones. So you build a system. You have users, products, and ratings. A simple matrix with users and movies being the corresponding row and column. But there's a problem. Your users' preferences change over time. The movie they loved last summer is not the one they want to watch in winter. The products trending now are different from those trending next month. If you ignore time, you lose this information. A 2D matrix can't capture temporal trends. So, you upgrade. Add a third axis. Now you have a tensor. Users times movies times time. Users along one axis, products along another. Time stacked in layers. Now the structure is preserved. Let's make this concrete. Suppose we have 4 users, 3 products, 5 time periods. That's a 4 by 3 by 5 tensor. Xijk is a single number, the rating of user I for product J at time K. This object has structure. 3 ways to navigate it, 3 ways to view it, and we're about to explore them all. A fiber is what you get when you fix 2 indices and free 1. It's a 1D vector living inside the tensor. For example, fix user I equals 0 and product J equals 0, but let time vary. That's a vector of 5 ratings, how this specific user rated this specific product over time. It's a 1D time fiber. Fibers are threads. Every fiber along the time axis runs parallel to that axis,
They're all identical in direction, just starting at different positions. If you fix just one coordinate instead, you get a slice. That gives you a matrix, but now it's a matrix with a very specific origin inside the larger tensor. It isn't just a generic table, it's one face of a higher dimensional object. Now sometimes you need to reshape. Unfolding converts a 3D tensor into a 2D matrix. Think of it like this. You take each fiber of the tensor and unfold it into a column of a matrix. For our 4 by 3 by 5 tensor, you end up with 4 by 15. 4 users along the rows, 15 superfeatures, products times time, along the columns. Why would you do this? Standard matrix methods, for example SVD, matrix factorization, and regression, only work on 2D data. If you want to use those tools, you unfold first. As AI scales, the amount of data and parameters explodes. We start small, just a modest amount of parameters. Watch what happens. What starts as a small tensor quickly grows into something massive. Billions, even trillions of parameters. This is where the practical issue shows up. Not just more data, but more data than a direct representation can comfortably hold or process. At this point, the problem is no longer how do we write the tensor down. It's how can we compress this massive data without losing information. Low-rank factorization is the move. Most tensors are redundant. Not all 1 billion parameters are independent. Many of them are linear combinations of a smaller set of core patterns. You cut the parameters from trillions to thousands, and the models still work. Sometimes better. This is an image, and this is where deep learning begins. When a neural network looks at a photo, it doesn't see a picture. It sees a tensor. Height, width, and 3 color channels: red, green, blue. But the network doesn't process raw pixels. It learns filters, small tensor slices that recognize patterns. Inside a convolutional neural network, the image passes through many convolutional layers. Each layer contains specialized filters. Now stack 16 filters together. You have a 4D tensor. Height, width, input channels, output channels. 64 filters, 64 detectors. Each emits its own feature map. One filter views 3 channels: red, green, and blue. This gives us Cin equals 3. The filter scans a 7 by 7 patch. These 3 channel responses sum into a single scalar at each spatial location. Combined, we get a weight tensor of 64 by 3 by 7 by 7. That's 9,408 parameters, nearly 10,000 numbers inside just this one layer. Here is the weight tensor W from the convolutional layer we just saw. It contains 9,408 individual numbers. Is it possible to store fewer parameters while still keeping most of the information? Instead of storing the entire heavy tensor, what if we could break it down into much smaller pieces? CP decomposition does exactly that. It represents the big tensor using 3 much smaller vectors. Next, we take the outer product of A and B. This produces a 2-dimensional matrix. When we take the outer product of that matrix with vector C, we get a 3-dimensional tensor. Of course, one component is not enough. We create multiple sets of these vectors, 5 different rank 1 terms in this example. Each set captures different patterns in the original tensor. We add all these rank 1 tensors together. The result is a very good approximation of the original weight tensor W, This powerful technique is called CP decomposition. Let's say you want to fine-tune a pre-trained model. It has 16 million parameters in its weights. To adapt it to your task, you update those weights. Gradient descent, backprop. Simple. But there's a problem. Storing 16 million weights, plus their gradients, plus optimizer states, that's a bunch of millions more numbers. And doing this for hundreds of layers? No, you don't do this.
Laura introduces a brilliant idea. Instead of updating the full giant matrix W, we freeze it and only train a much smaller low-rank update. Delta W approximates B times A, where the rank is very small. By choosing a very small rank, for example, R equals 8, the number of trainable parameters drops dramatically. Let's compare the numbers. The full weight matrix has over 16 million parameters. With Laura, we only need around 65,000 trainable parameters. That's a 256 times reduction in the number of trainable parameters. In polynomial networks, the input doesn't just pass through, it interacts with itself. Every element of the vector x multiplies with every other element. This is the outer product. X tensor x. We don't stop at second order. We can keep multiplying the input by itself, creating higher order tensors. Third order, fourth order, and beyond. To get the final output, we perform a tensor contraction between the learned weight tensor and this high order input tensor. All those complex interactions are summarized into a single output value y. This is the core operation of polynomial networks. Here's why this matters. A traditional linear model can only draw a straight line. It fails on complex patterns. But when the network can capture higher order interactions through tensor products, it can create rich, curved decision boundaries that perfectly separate even difficult clusters. So far, we've seen tensors as containers of numbers. When we factorize a tensor, we're actually discovering an equivalent computational circuit. Multiplication nodes combine features, while summation nodes mix different options. This circuit computes the same result as the original tensor. Data flows through this circuit. Inputs are multiplied together to create interactions, then summed to produce the final output. Multiplication nodes combine features, while summation nodes mix different options. Now comes the crucial insight. We can build the same function using very different circuits. A shallow circuit needs many direct connections, but requires exponentially many parameters. A deep circuit builds the same result step by step, layer by layer, is dramatically more efficient, needing only linearly many parameters. Depth gives us enormous savings. This is one of the most powerful ideas in modern AI. When you combine tensor factorization with deeper circuits, you get models that are both more expressive and far more efficient. Depth plus tensors equal real AI power. Standard self-attention has a massive hidden cost. Every token has to attend to every other token. For a sequence of length n equals 512, that means creating and storing over 262,000 relationships. But what if we change the order of computation? What if we remove the softmax and rearrange the operations? Now, we first compute phi of kt times v, a tiny d by d matrix, where d is much smaller than n. Suddenly, the massive n by n grid is no longer needed. We've reduced the complexity from quadratic to linear. Look at the geometric difference. On the left is the classic attention maze, every token connected to every other, a complete mess of crossings. On the right is the polynomial version. Each token travels in its own clean parallel lane. No crossings, no quadratic explosion, just pure linear flow.
For n equals 512, standard attention requires 262,144 operations. The polynomial version needs only 512. That's over 500 times fewer computations. And for really long sequences, 1,000 times longer, the memory savings become enormous. This is the power of smart tensor reordering.
During training, after the forward pass comes the backward pass. This is where gradients are computed for every single weight in the model. The problem? The raw gradient tensor, delta W, is often just as large as the model itself. It consumes enormous amounts of memory, sometimes even more than the parameters. The solution is to factorize the gradient using tensor decomposition. Instead of storing the full dense gradient, we decompose it into a small dense core tensor and several thin factor matrices. This is Tucker decomposition applied directly to the gradients. We keep the essential information while throwing away redundancy. Look at the memory impact. The raw gradient takes up 100% of the memory. After factorization, we only need about 20% of that space. This gives us a 5x reduction in gradient memory. Now we can train much larger models on the same GPU. The key idea is elegant. We approximate the gradient as a small core tensor multiplied by thin factor matrices. The core captures the essence, while the factors handle the main directions. This clever tensor trick lets us train large models more efficiently without sacrificing much quality.
Tensor factorization is not just a math trick. It's a powerful lens that helps us decode complex real-world data. Let's look at two practical examples. Imagine you're at a noisy cocktail party. 3 people are speaking at the same time, and all you have are mixed microphone recordings. This creates a complex tensor of frequency, time, and microphone channels. Using tensor factorization, we can blindly separate the mixed signals back into the original individual sources, without ever knowing what they were in advance. This is called blind source separation. Now let's move to recommendation systems. We have a tensor of user behavior across products and time, but many entries are missing. Non-negative tensor factorization breaks this tensor into interpretable factors. Each factor corresponds to real human patterns: teenagers who love games, adults who buy books, or users who respond to tech promotions. Because we enforce non-negativity, every component has a clear, meaningful, real-world interpretation. Even better, once we have the factors, we can complete the tensor. We predict the missing values with high accuracy. In practice, you often only need 20% of the actual data to reliably fill in the remaining 80%. This is incredibly powerful for sparse real-world datasets.
Tensor factorization becomes even more powerful when we couple multiple data sources together. With coupled tensor factorization, we can analyze multiple datasets that share common dimensions. Here we have a 3D tensor of user behavior over time, and a 2D matrix of user demographics. They share the same user factor. This shared factor acts like a bridge, allowing information to flow between the two data sources. By solving them jointly, we gain a much richer understanding of users from multiple perspectives. In healthcare, we can couple patient records across symptoms and time to detect hidden disease patterns early. On social media, tensor factorization helps uncover emerging trends and hidden communities from user hashtag interactions over time. In transportation, we can predict traffic congestion by analyzing location, flow, and time together. From healthcare to social media to transportation and beyond, tensor factorization serves as a universal lens. Any multidimensional real-world data can be powerfully decoded using tensors.
As we reach the end of this journey, let's bring everything together. All these ideas are united by one fundamental operation: the low-rank tensor decomposition. Complex structures emerge from simple components. AI is not magic. It is geometry. Tensors are how we structure the vast universe of data. Low-rank decomposition is how we discover its hidden essence. Thank you for joining us on this journey through the world of tensors.
We hope you now see that behind every powerful AI system lies beautiful, elegant mathematics, built from simple numbers into structures that can understand our world.